In this lecture, we're going to talk about when a vector field is conservative, and we're going to use the fundamental theorem of line integrals to give a characterization of this. So let's let F be a vector field on a domain D in any number of dimensions. Theorem: F is conservative, meaning vector field F is the gradient of some potential function f, if and only if the line integral over C of f dot dr equals 0 for every closed curve in the domain D. Okay, so we're going to prove this. In order to prove this, we've actually got two things to prove, because if you look at the statement, you see an if and only if, which means that the if-then should work both ways. Okay, one of these is going to be very simple to prove because we've actually already talked about it and discussed why it's true. And that is, okay, so let's say proof number 1, or for one of the if-then statements. And that statement is if f is conservative, then the line integral over C of f dot dr equals 0 for all closed curves C in the domain D. Well, we already talked about that. If f is conservative, then f dot dr equals gradient f dot dr. And we, gradient f is going to integrate, let's actually turn this from A to B, I should say. Let me write this properly. So this would be gradient f of r of t dot r prime of t dt. But gradient f integrates to f. So this would integrate to f of b minus f of a. But if C is a closed curve, then A and B are equal. Therefore, that equals 0. And we already talked about that in the previous lecture segment from the fundamental theorem of line integrals. So the more challenging one to prove is going to be the second statement. So the second statement that we now want to prove is, let's call this proof 2. And that would be the if-then statement in the opposite direction. If the line integral over C of f dot dr equals 0 for all curves C in the domain D, then F is a conservative vector field. Or F equals gradient F. Okay. So now let's go ahead and prove this one. So our assumption, or our given, is the if part of that. So the line integral over C of f dot dr equals 0 for all closed curves C in the domain D. Okay? And what we need to do is we need to find a potential function f on this domain D such that the vector field f equals gradient f. Okay, just for ease, we're going to let D be a domain on R2. So it's easier for me to draw a diagram, but general cases in higher dimensions are similar, okay? All right, and then we're going to general cases in higher dimensions are analogous. Okay. And then we need to come up with a potential function. Okay, so let's call f of x, y. Let's let f of x, y equal the line integral over c of f dot dr, where c is a curve that goes from the point 0, 0 to the point xy. And again, just to make it a little bit easier, I'm going to say x and y are positive values. Okay, so normally I would say, well, what c are you talking about? Because I really haven't talked about anything specific for the curve that goes from 0, 0 to xy. So why is this path independent? Why does it not matter which curve C I pick to go from 0, 0 to xy? Okay, so let's draw a picture. All right, so okay, so we're going from 0, 0 to some point xy. Okay. And let's say that here is my curve C. Okay, and my curve goes, again, from 0, 0 to xy. Well then, let's find another path. I've arbitrarily picked C, but let's find another path, and let's call that path C prime. So maybe C prime is over here, and C prime also goes from 0, 0 to xy. Well, I need to show that it doesn't matter which path I pick. This is, C could be either of these. So what I want to show is that then I want to show that those two paths will give the same value in my function. So I want to show that the line integral over C of f dot dr is equal to the line integral over C prime of f dot dr. Okay, so if these are equal, then my integral and little f is independent of path. Okay, so by drawing both C and C prime, I've actually created a closed curve, right? Okay, so let's draw a picture of that. So my closed curve is, let's go back here, x, y, this is 0, 0, x, y. So my closed curve starts and ends at 0, 0, okay? And it's going to go along C, okay? And it's going to return to 0, 0 along negative C prime. Okay, so now I have a closed curve. So my closed curve is C plus negative C prime, or C minus C prime. Well, the assumption in this proof is that the line integral over f dr, right? The assumption is that, if we go back to the top of the page here, is that, let's go right up here. Here's my assumption. The assumption is that the line integral over C of f dot dr equals 0 for all closed curves in the domain. Well, that means that the integral over C of f dot dr minus the integral over C prime of f dot dr is 0. So my closed curve again is C minus C prime. Okay, so therefore, I've shown that that this right here, the function that I've defined as my potential, is well-defined and independent of path. So that's the first step here. Okay, so it's reasonable to define my function f in this way. Okay, now the next thing we need to prove, and I'll go over to the next page here, we need to prove that vector field f equals gradient f to show that it is conservative. Okay, so next step here. So again, we want to prove vector field f equals gradient f, okay? And let's call vector field f pq, p of xy, q of xy. Okay, so if we want to prove that these two things are equal, we want to prove that PQ equals partial f, partial x, partial f, partial y. Or in other words, P equals partial f, partial x, and Q equals partial f, partial y. Okay, so I should have started out by saying that f is, I want to assume that f is a differentiable vector field. Differentiable vector field. Okay. All right, so let's prove this. F is a differential vector field. C is a curve going from 0, 0 to xy. Okay, so I'm going to draw that picture again. And I've proved that this is path independent, so I can pick any path I want now to go from 0, 0 to xy. Okay, so I'm just going to start with P equals f of x, partial f partial x first. Okay. The proof for Q is analogous. I'll just do that sort of quickly after this one. All right, so I'm going to pick a path, C, that goes from 0, 0 vertically, and then that goes horizontally to xy. So I'm going to call this first leg C1, and this is going to the point 0y, and then I'll call this second leg C2. And so the f of xy, which is, remember we defined this function as the line integral over c of f dot dr. Well, that's going to be the sum of my two segments. So the line integral over c1 of f dot dr plus the line integral over c2 of f dot dr. Okay, so let's look at our parameterizations. For C1, R of t is 0t, and t goes from 0 to y. And then for C2, R of t is ty, and t is going from 0 to x. Okay. So now I'm going to say that f of xy equals, well, f dot dr. Well, f is, so for C1, this is going to be the integral from 0 to y. F is pq, and then r prime of t is going to be 0, 1. Plus, the second integral for C2 is going to be the integral from 0 to x of pq. And then dot, r prime for C2 is 1, 0. So let's multiply these out. And I'm going to get the integral from 0 to y. So this is going to be 0 plus q. So just q x of t, y of t, dt, plus, this is going to be p plus 0. So the integral from 0 to x, p x of t, y of t, dt. Well, now the results from both of these integrals, this first integral is going to be a function of y. The second integral is going to be a function of x. Okay, now remember, I'm trying to prove p equals partial f partial x. So now, if I take the derivative with respect to x to find partial f partial x, well, this is going to be 0 because since I'm differentiating with respect to x, y is treated as a constant. And then plus the derivative with respect to x of the integral from 0 to x of p of x of t, y of t, dt. And then, so for this part, for this part right here, you just apply the fundamental theorem of calculus and you get p, right? So this now gives me that partial f partial x equals p of xy. And that was what I had set out to prove, or at least the first part of what we're trying to prove here. So the first component of vector field f equals the first component of gradient f. And so now I'm just going to pretty quickly run through the y, prove q equals partial f partial y. It's completely analogous, so we don't have to go through every detail. but I'm going to choose a slightly different path here. So here's my 0, 0 point. Here's my XY point. Now this time I'm going to go horizontally first and then vertically. Okay, so I'm going to call this C3 and I'm going to call this C4. Okay, and I have this point here, X0. Okay, so my parameterization for C3, okay, what's that going to be? That's going to be T0 for T is from 0 to X. And then C4 is XT, and T is from 0 to Y. And remember, I'm trying to prove that Q equals partial F partial Y. So I have F of XY equals, my first integral is from 0 to X, PQ dot 10 dt, plus the second integral is 0 to Y, PQ dot 01 dt. So this is going to give me the integral from 0 to X of P dt. Let's write this properly. X of T, Y of T, dt, plus the integral from 0 to Y of Q, X of T, Y of T, dt. And again, when after you integrate, this is going to give you a function of X. And the second integral is going to give you a function of Y. And so now I'm trying to prove that the partial derivative with respect to Y is equal to something. So I want to differentiate with respect to Y. So therefore, I'm going to get a 0 because the first integral is a function of X, and now X is being treated as a constant. And then for the second integral, after we take the derivative with respect to Y of an integral and apply the fundamental theorem of calculus, we are just going to get Q. And so I get Q, or df dy equals Q of x, y. Okay, so if you take the result on this page and the result on the previous page, we have achieved what we set out to do, which was we showed that PQ equals partial f partial x partial f partial y, and therefore f is conservative because we have shown that f is equal to the gradient of a potential function little f. Okay, so if we go back to the very beginning, what were we trying to do here? We were trying to prove the theorem that if f is conservative, f is conservative if and only if the line integral of f dot dr equals 0 for every closed curve in the domain D. We had already shown that. The first part when we talked about the fundamental theorem of line integrals. So this first proof was actually very straightforward because we have already done the work for it in a previous lecture. And then for the second proof, we want to show that if f dot d, the line integral over C of f dot dr is 0 for every closed curve C in the domain D, then f must be conservative. So we defined a potential function f, and then we proved that the partial derivatives of f are the components of vector field f.